Welcome back to the Deep Dive. Today, we are taking a very different approach. We've got our hands on the official Power Battery Technology RoadMap, RoadMap 3.0, and we're going to treat it like a top-tier consultancy report.
Exactly. Our mission here is to really dissect this document, to understand the strategic intent behind it. We're not just looking at the goals for 2040, but the underlying bets they're placing to try and secure global leadership.
And when the sources talk about power batteries, they make it crystal clear we're not just talking about a car part.
Not at all.
They're defined as the absolute core of this huge automotive revolution that's happening right now. Electrification, connectivity, all of it. This roadmap, it's not about small tweaks to cars.
No, this is about reshaping the entire energy and transportation system, and that's why the stakes are just so incredibly high. The document literally calls this the next generation technology high ground.
It's not just a commercial competition then.
And it's far beyond that. It's a race for national security, for economic dominance. You can see countries locking in these detailed national strategies right now.
And you see that pressure in the examples they cite. Take the U.S. National Lithium Battery Blueprint. It's so pragmatic.
It is. It's all about resilience. Secure the supply chain, bring manufacturing back home, and crucially, drive down the cost aggressively.
And they mention a specific cost target.
They do, and this is a key piece of intelligence. The U.S. is aiming for $60 per kilowatt hour.
$60. So why that number specifically?
Well, $60 isn't just a random number. It's seen as the tipping point, the price where an EV becomes truly cost competitive with a gasoline car across almost every segment without needing massive government subsidies. It's the number for mass adoption.
Okay, so that's the U.S. strategy. Then you have the European Union, and they're coming at it from a totally different angle, more regulatory.
A completely different playbook. They have their Green Deal industrial plan and the big one, the new battery law, which is mandatory from August of this year, 2024.
And this law is a huge strategic lever, isn't it?
It's a formidable one. It basically dictates the rules of the game for anyone who wants to sell in the EU. It's not just about performance. It forces you to secure local supply chains, and this is the critical part, it puts these incredibly strict, auditable requirements on the carbon footprint of every single battery.
So you have to green your entire supply chain just to get access to their market.
Exactly. They're weaponizing environmental standards to drive industrial policy. It's a very clever, very powerful move.
And then we pivot over to Asia. And there, the game seems to be all about the next big technological leap.
All about it, specifically all solid-state batteries. Japan's strategy from 2022 is explicitly focused on getting all solid-state lithium batteries to full commercialization around 2030.
And Korea is even more aggressive.
They're on an absolute sprint. Their strategy aims to get automotive solid-state batteries commercialized as early as 2026.
2026.
Yeah.
Wow.
It shows this global race is being driven by that promise of, intrinsic safety and the huge jump in energy density that solid-state offers.
So that sets the stage perfectly. Our mission today is to unpack the master strategy inside this Roadmap 3.0. We'll break down the 6 key pillars of the 2040 vision, we'll get into the hard numbers of their dual-track strategy, and really understand the whole blueprint for leadership. Okay, let's unpack this. Before we get lost in the moonshot goals for 2040, a good analysis always has to start with the baseline. Where are we today in 2024? Did the industry even meet its near-term 2025 goals?
Well, this is where it gets really interesting. The data shows that the industry isn't just on track, it's accelerating. It's moving faster than even the ambitious projections from a few years ago.
So they're ahead of schedule.
They are. Many of those 2025 targets are either already met or, as the document says, nearing completion, way ahead of time. And that validated strength, that momentum, is the launch pad for this much more aggressive 2040 vision.
Let's get into the specifics then. What about the core cell performance, the numbers that actually matter for range and power?
Okay, so we can break it into 2 tracks. For the mass market cells, what they call popularity or economic cells.
The affordable ones.
The affordable ones, exactly. The 2025 target was to get over 200 watt-hours per kilogram, and that's been comfortably beaten. Today's production is already hitting between 200 and 220.
And that includes LFP batteries too.
Yes, which is a big deal. Even LFP, phosphoric iron lithium, is routinely getting up to 210 weight kmj. That really expands where you can use that chemistry.
Okay, so what about the other end of the market? The high-end premium cells, usually the high-nickel NCM chemistries.
Right. For those, the 2025 target was to get above 350 weight kmj. The report calls this near completion.
Meaning they're not quite there yet.
Not quite in mass production, but very close. Widespread industry operations are delivering in the 280 to 350 WHKM range. The trajectory is clear. Hitting 350 is imminent. It shows they're squeezing just about every last drop of performance out of the current liquid chemistry.
Performance isn't just about range, though. Fast charging is maybe even more important for getting people to switch. How are we doing there?
The progress on fast charging is probably the most significant achievement for the user. The 2025 target was to get from a 10% to an 80% charge in under 15 minutes.
And that's been met.
That's been met. Current commercial systems are clocking in between 10 and 15 minutes.
You mentioned LFP earlier. That chemistry wasn't traditionally known for its speed.
And that's the strategic breakthrough here. The source specifically notes that LFP batteries have smashed through the 4C to 6C charging barrier. Some are even capable of hitting 10C.
10C, what does that mean in plain English?
A 10C rate means you could theoretically charge the entire battery in 1/10 of an hour, so 6 minutes.
Wow.
It completely changes the game for LFP, making it a real contender for fast charge applications where it couldn't compete before.
Okay, so that's the current liquid battery tech. What about the next generation solid state? How are the prototypes looking?
The progress here is really what gives them the confidence for the 2040 vision. The energy density target for solid state in 2025 was over 400 Wh/kg. They've already hit it. Current prototypes are sitting between 400 and 500 Wh/kg, so the tech is not just a theory anymore.
Are there specific companies leading this?
The source mentions a few. QuantumScape in the US is one, but it also points to major players like CATL, BYD, and Wyland, who are all talking about small batch production or even mass production around 2026, 2027.
This is all great tech, but at the end of the day, market leadership comes down to cost and scale. How is the manufacturing side doing?
This might be the most important early win of all. The cost targets were met early. The goal was to get manufacturing cost under 0.1 yuan per watt hour.
And they hit that.
They beat it. 2024 performance is even lower, somewhere between 0.07 and 0.08 yuan per batch. That cost advantage is a massive competitive weapon.
And can they make them fast enough?
Yeah.
What about scale?
Scale has blown past expectations. The 2025 target for a single production line was a capacity over 2 gigawatt hours per line. That's been easily met.
What are the best lines doing now?
The industry-leading lines are already hitting 8 to 10 gigawatt hours.
Just to put that in perspective for you, 10 gigawatt hours is enough capacity for, what, over 100,000 EVs a year?
Roughly, yeah. Maybe 100,000 to 150,000, depending on the car. All from a single automated line. It's this combination of cost and scale that gives them this huge, validated head start.
It sounds like they're not just progressing, they're accelerating. They've built this incredibly strong foundation, and now they're using that momentum to launch this even more ambitious vision for 2040.
Right. And if we look at that 2040 strategy, the vision is not just about making a better battery. It's a fundamental reimagining of what a battery is. They want to evolve it from a passive box that holds energy into what they call an intelligent body.
Intelligent body. That sounds like something out of science fiction. What does that actually mean?
It means the battery itself becomes an active, self-aware part of the vehicle. It's fully integrated into the car's digital nervous system and even the energy grid. It has to have its own operational intelligence.
Okay, so to get there, this isn't just a single path.
No, it's a six-pronged attack. The roadmap lays out 6 strategic dimensions they have to make breakthroughs in, all at the same time, over the next 2 decades.
Let's walk through them. The first one has to be about range, right? The number one thing people worry about with EVs.
Absolutely. Dimension 1 is the energy density breakthrough. The goal is simple. Eliminate range anxiety completely. Get to a point where EVs can fully replace gasoline cars in every single use case.
Not just cars, but trucks. Maybe even planes.
Exactly. Heavy-duty commercial vehicles, long-haul logistics, maybe even short-haul aviation. Everything.
Okay, so that's dimension 1. What's the second? Safety has to be high on the list.
It's number 2. They call it the intrinsic safety revolution. The strategy here is to move away from the current way of doing things, which is just adding layers of protection sensors, cooling systems, armor plating.
Right.
The new approach is to embed safety directly into the core materials and the cell design itself. If the battery is inherently safe, you don't need all that complex, heavy, and expensive protection.
Makes sense. So dimensions 3 and 4 must be about the ownership experience, cost and convenience.
Precisely. The third is sustained cost reduction. We've seen them have early success, but for the future, they need radical innovation. New, cheaper materials, ultra-efficient manufacturing.
And the fourth?
The user experience upgrade, this is a tough one. It demands achieving two goals that are usually contradictory. You need extreme fast charging and an exceptionally long lifespan at the same time.
Yeah, usually if you charge a battery super fast all the time, it degrades much quicker.
It does. The 2040 vision says you have to master both. No compromises.
And the last two dimensions feel very modern, very much about today's global landscape. Sustainability and intelligence.
They're absolutely essential, especially with rules like the EU's new battery law coming in. So the fifth is full life cycle carbon neutrality. This means building a truly green supply chain from mining the raw materials all the way through to manufacturing, use, and recycling.
So the battle isn't just on performance, it's on your environmental footprint.
It becomes a key competitive metric, and that leads directly to the sixth and final dimension, intelligent integration. This is the heart of that intelligent body idea.
What does that look like in practice?
It means the battery has to have self-sensing, self-repair, and self-adaptive capabilities. It can monitor its own health at a micro level, diagnose problems before they happen, and then autonomously adjust how it operates to maximize its own performance and lifespan. It's a battery that takes care of itself.
So we have this big visionary goal of the intelligent body. But visions are one thing, hard numbers are another. The roadmap puts some concrete, measurable targets on this. And it does it with a really interesting dual-track strategy.
Yes, this dual-track approach is very clever from a market standpoint. It recognizes that the mass market and the premium market have totally different needs.
So it lets them chase the moonshot without ignoring the high-volume stuff.
Exactly. They can keep winning in the here and now while they invest in the high-risk, high-reward future.
Okay, let's start with track one. High energy density. This is the moonshot track, right? For the premium cars, the big trucks, anything where weight is the enemy.
This is where the science gets really radical.
Right.
So by 2030, the target for mass energy density is equal to or greater than 500 watt-hours per kilogram.
500, that's a huge jump from where we are today.
A massive jump. And for volume density, it's over 1,000 watt-hours per liter. Then, just 5 years later, in 2035, it goes up again. 600 waste kilograms and 1,200 watt-HL.
And what's the ultimate peak target for 2040?
The 2040 goal is just stunning. A mass density of at least 700 watt-H kilogram and a volume density of 1,400 watt-HL.
And it still has to last, right? What about cycle life?
It still has to be a viable product. They're targeting at least 1,500 cycles over a 10-year life. But make no mistake, hitting 700 watt-H means one thing. They have successfully commercialized all solid-state batteries with things like lithium metal anodes. It's a complete game changer.
Okay, so that's the high end. Now let's look at track two. High cost effectiveness. This is for the mass market, the fleet vehicles.
Correct. Here, the focus completely shifts to affordability and durability. So for 2030, the goals are more modest. 250 watt-HL for mass density and 500 watt-HL for volume density. Still a nice improvement, but pragmatic.
But the real story for this track seems to be longevity.
That's the core value proposition. The cycle life target is an incredibly long 3,000 cycles over a 15-year life.
15 years, that's huge for fleet managers or anyone worried about resale value.
It guarantees it. And then by 2040, they want to bump the performance up to 350 watt-HL and 700 watt-HL while keeping that exceptional 15-year life.
So basically, today's high-end performance becomes the standard affordable option in 20 years.
That's the goal.
It's obvious that hitting these targets on both tracks at the same time requires a massive coordinated effort. Which brings us to the structure of the whole roadmap, the 7 core pillars.
Right. These 7 pillars are the operational framework. They define every technical and industrial capability they have to master all at once. It covers everything from key materials and cell design all the way to manufacturing, recycling, and the carbon footprint. They need breakthroughs in all 7 areas.
So we have to dive into those breakthroughs, starting with the most fundamental, Pillar 1, the key materials revolution. I mean, to get to 700 watt-HK, you can't just tweak what we have now. You need entirely new chemistry.
You do. This is where the roadmap places its biggest and riskiest bets. Current materials, like the graphite in your anode, are basically at their theoretical limit. So the focus has to be on replacing those core components.
Let's start with the cathode, the positive side.
Yeah.
How do you get more capacity there?
Well, the current chemistries, NCM and LFP, will keep getting better through engineering. For LFP, it's all about packing it in tighter, pushing the physical press density to over 2.8 grams per cubic centimeter by 2040.
And for the high-energy track?
For that, the long-term shift is pretty radical. They're moving toward what's called Li-rich manganese-based oxides. These have the potential for a much higher specific capacity, targeting over 300 milliamp hours per gram by 2040.
And the big advantage there is less reliance on cobalt and nickel.
That's the strategic play. You reduce your dependence on those expensive, geopolitically tricky metals, while at the same time you're fundamentally boosting your energy storage.
But I've heard those materials have had big problems with stability and voltage fade over time.
They have. So hitting that 300 milliamp target implies they have solved those exact problems, probably with new coatings or surface modifications to keep the material structure from falling apart over thousands of cycles.
Okay, now for the anode, the negative side.
Yeah.
Everyone agrees this is the real bottleneck for super high density.
It absolutely is. The anode has to move far away from graphite. The main focus is on silicon-carbon composites.
And the potential there is massive, right?
It's enormous. Graphite gives you about 372 millitag. The roadmap sets a target for silicon carbon to hit over 3,200 millitag by 2040. That's almost a tenfold increase. You can't get to 700 weightage without it.
But the famous problem with silicon is that it swells up like crazy when you charge it, which just destroys the battery.
Right, it can swell up to 400%. So the roadmap sets these really aggressive engineering goals to control that. They want to limit the volume expansion to under 90% in 2030 and then push it down to an incredibly difficult 60% by 2040.
How do you even do that?
It requires some really sophisticated nanostructuring of the silicon itself, plus creating new, highly elastic binder materials that can hold everything together while it flexes. It's deep, deep material engineering.
And what about the ultimate prize, just using pure lithium metal?
That's the end goal, the non-negotiable target, mainly for the all-solid-state cells. The roadmap aims to get its surface capacity up to over 4 milliamp hours per square centimeter by 2040. The whole challenge there is stopping the growth of dendrites, those tiny metal spikes that cause short circuits.
Which is why you need a solid electrolyte to block them.
Precisely. Which brings us to the solid electrolytes. This is the key safety enabler. The roadmap is looking at a few different types, but the current frontrunner is the sulfide-based ones.
Why sulfides?
Because they have the highest ionic conductivity. The ions move through them quickly. The target is to get their room temperature conductivity up to over 2.0 times 10 to the minus 2 Siemens per centimeter by 2040.
And why is that specific number so important?
Because if the conductivity is too low, the battery can't deliver power quickly. It can hold a lot of energy, but you can't get it out fast. Hitting that number means a solid-state battery could potentially charge and discharge as fast or faster than today's liquid batteries. That's a must for cars. But, and this is a big but, the source notes that sulfides have a major stability problem. They react with air and moisture, which makes them a nightmare to manufacture at scale. Solving that is one of the biggest hurdles in this entire roadmap.
So moving from the raw materials in Pillar 1 to the actual engineering in Pillars 2 and 3 cell design and system integration, the roadmap lays out a very clear step-by-step evolution. It seems designed to manage risk.
It's a very strategic phasing. They know you can't just jump to the end goal overnight. So first, you have the current liquid-ion batteries. They're going to keep optimizing those for the short and midterm, pushing for higher nickel, higher voltage, and really nailing extreme fast charging. They want the high-end liquid cells to hit that 10-minute charge time from 10 to 80% by 2040.
But the really interesting step seems to be the one in the middle, the hybrid solid-liquid battery. That feels like a crucial bridging technology.
It is. It's a way to get some of the benefits of solid state, better safety, higher density without having to solve all the massive manufacturing challenges at once. And it's already happening. Some companies are hitting 360 Wh/kg with these hybrids today.
And the goal is to push that even further.
The target is to get these hybrids up to over 550 Wh/kg by 2040. It basically buys you time and performance while the all-solid-state research matures.
Yeah. Which is the final destination for the high-energy track.
The all-solid-state battery is the non-negotiable end goal. It's the only way they see to hit those 700 Wh/kg targets and, critically, to achieve that goal of intrinsic safety.
How do they measure intrinsic safety for solid state?
One key metric is thermal resilience. The cell has to be stable in a thermal box test up to at least 300 degrees Celsius by 2040. If a battery can take that much heat without bursting into flames, it just fundamentally changes vehicle design and safety rules.
The roadmap also mentions a long-shot technology, lithium-sulfur.
It does. Li-S has an even higher theoretical density with a crazy target of over 800 Wh/kg by 2040. But the source is very clear that it's still a science project. The cycle life is a huge problem right now. It's like a parallel research track, just in case.
Okay, let's switch gears to system integration, Pillar 3. This is all about how you actually pack the cells into the car, and it's an alphabet soup of acronyms. CTP, CTC, CTC.
Yes, let's decode that for you. It's all about efficiency. CTP is cell to pack, where you eliminate the modules inside a traditional battery pack. CTC is cell to chassis, where the battery pack becomes a structural part of the car's floor. And CTB is cell to body, integrating the cells directly into the vehicle's core structure.
And there's a metric for this, GDA.
Right. Group density achievement. It's basically a measure of how much of your final battery pack is actually active battery cells versus casing, cooling, and electronics. The goal is to get that GDA number to over 90% for both mass and volume by 2040. Almost no wasted space.
The language around safety in this section is really powerful, moving from protection to prevention.
It's a total strategic shift. We're moving away from the current standard, which is just make sure a fire doesn't spread for 30 minutes, to the ultimate goal for 2035-2040. NO thermal runaway, period.
And to prevent something, you have to see it coming. The pre-warning capability target seems almost impossible.
Yeah.
7 days.
It is an incredible goal. Today's systems might give you a 5-minute warning. The RoadMap wants to get that to 3 hours by 2030, and then that unbelievable 7 days of pre-warning time by 2040.
How is that even technically possible?
It requires a massive leap in AI and sensing. The battery management system, the BMS, has to become a true digital twin of the physical battery. It has to be constantly analyzing huge amounts of data from inside the cells to detect these tiny, subtle changes that happen a week before a failure.
The strategic impact of a 7-day warning would be enormous.
Game-changing. You can schedule maintenance, take the vehicle out of service, swap the battery. It changes everything about insurance, liability, and warranties.
And to get that kind of foresight, you need way more sensors and much smarter software.
That's the intelligence part. First, sensing. The RoadMap wants to increase the ratio of sensors to cells from maybe 1 for every 6 cells in 2030 to 1 for every 2 cells by 2040. So you're getting this incredibly detailed, real-time map of the battery's health.
And the software side, the over-the-air updates.
The OTA capability has to evolve. It goes from L3, which is basically self-diagnosis, to L5, intelligent self-adaptive optimization, by 2040.
L5. So the battery thinks for itself.
Completely. It learns your driving habits, it knows the weather, it tracks its own degradation, and it autonomously changes its charging and discharging strategy to maximize its own lifespan and performance. It becomes a truly intelligent body.
You can have the most amazing cell design in the world, but if you can't build it perfectly, cheaply, and at massive scale, it doesn't matter. This brings us to Pillar 4, extreme manufacturing.
Right, and the roadmap is very clear that this is where you convert a technical advantage into a real durable market advantage. They talk about reaching the limit of manufacturing.
Let's talk about quality first. With these new, complex, and sometimes sensitive materials, the defect rate has to be near zero.
Near zero is an understatement. The target for the cell yield rate, the percentage of good cells that come off the line, is set to hit greater than or equal to 99.99% by 2040.
99.99%, what does that even mean?
It means a defect rate measured in parts per billion, maybe one bad cell for every 10 million you make. It's a level of quality that is just unheard of in most mass production. And it's the only way you make these new chemistries affordable because you have virtually zero waste.
So quality drives cost. What about other efficiencies?
Material utilization is key. They're targeting over 98% utilization by 2040, so almost no raw material is wasted. And the direct manufacturing cost has to keep falling, down to less than 0.04 yuan per watt hour by 2040.
And you have to do all that while going faster.
Much faster. They're targeting huge accelerations. For example, the coating speed, which is often the bottleneck, needs to go from over 180 meters per minute in 2030 to over 300 meters per minute in 2040.
And stacking, putting the layers together.
Stacking efficiency has to jump from over 800 pieces per minute in 2030 to a mind-boggling 2,000 pieces per minute by 2040.
And the ultimate vision for this is the fully automated factory.
It is. The goal is to create blackout factories by 2040. These are facilities so automated, so digitized, that they can run in complete darkness with no people on the floor. Everything is controlled by big data models and digital twins that are constantly optimizing the process.
Okay, let's shift to Pillar 5, R&D tools and testing. This feels like it's about owning the innovation process itself.
That's exactly what it is. It's a strategy for achieving R&D sovereignty. The goal is to develop a complete domestic R&D tool chain, all the software, all the simulation models that covers the entire life cycle. This means you're not dependent on anyone else's tools or knowledge. You control your own pace of innovation.
And the complexity of what they need to model is huge.
Immense. The focus is on what they call multi-physical field coupling simulation. That means building models that can simulate the electrical, thermal, and mechanical forces all at once and see how they interact. Because what happens electrically creates heat, the heat causes physical stress, and the stress changes the electrical performance.
It's all connected.
It's all connected, and being able to model that accurately allows you to do virtual testing and build those digital twins we talked about, which can predict safety and lifespan with incredible accuracy.
And on the physical testing side, how do you check these new materials without destroying them?
You need advanced, non-destructive, and online testing methods. And the source gives a really specific, really important target: developing online lithium plating detection with an accuracy of over 99% by 2040.
Why is that one thing so critical?
Because lithium plating is the silent killer of batteries. It's what causes them to degrade, to lose their fast charging ability, and eventually to fail. If you can detect it happening with 99% accuracy as the battery is being made or used, you can prevent it. It's absolutely essential for reaching that 15-year lifespan goal for the mass market batteries.
Okay, that brings us to our final two pillars, which are all about the environment and resource security. Pillar 6, recycling and reuse, and Pillar 7, the carbon footprint. This feels like a direct response to global regulations, especially from Europe.
It is. This is about building a circular green ecosystem that ensures you have the resources you need for the long term and that you can sell your products anywhere in the world. The strategy has two parts: reuse and regeneration.
Let's start with reuse, or what they call hierarchical utilization, giving old EV batteries a second life.
Right. The biggest challenge there is figuring out how much life is actually left in a used battery. So they need to develop really good non-destructive diagnostic tools. The target is ambitious. By 2040, 80% of all collected waste batteries should go into a second-use application first.
Like for home energy storage or something.
Exactly. Grid storage, industrial equipment, backup power. It creates a whole new value chain.
And for the batteries that can't be reused, that's regeneration or recycling.
Yes, breaking them down to get the raw materials back. The focus is on hydrometallurgy, and the recovery targets are extremely high.
What are the numbers?
By 2040, they want to recover over 99% of the nickel, cobalt, and manganese. For lithium, the target is over 95%. This isn't just about being green, it's about national security. Every ton of metal you recycle is a ton you don't have to import.
But the roadmap points out a big problem here. What about all the new chemistries?
That's the forward-looking part. A huge task is to figure out how to economically recycle all solid-state batteries, or anodes, with high silicon content. The current processes aren't designed for them. You have to invent and scale up new recycling technologies before those new batteries hit the market in huge volumes.
And finally, Pillar 7, the full life cycle carbon footprint. This is the big one for market access.
This is the ultimate test of green leadership. The goal is to reduce the total carbon footprint of both NCM and LFP battery systems by a massive 60 to 70% compared to 2020 levels by 2040.
60 to 70%. How on earth do you achieve that?
It really comes down to two huge levers. The first is production decarbonization. They have to switch their factories to clean energy. The target is to use over 80% clean or renewable energy in the cell production stage by 2040.
So massive investment in solar, wind, and hydro for the factories themselves.
Huge investment. The second lever ties right back to Pillar 6. It's about closing the loop and using more recycled materials.
What are the targets for recycled content?
At 2040, they want new batteries to contain at least 15% recycled lithium and 15% recycled nickel.
And I noticed the target for cobalt is much higher.
It is. The target for the cobalt circular material usage ratio is over 30%. That reflects how valuable, toxic, and geopolitically sensitive the cobalt supply chain is. Using more recycled cobalt gives you the biggest strategic bang for your buck.
So we've gone through this entire roadmap. The goals are just massive. 700-way HT cells, L5 autonomous batteries, the insane 99.99% manufacturing yield. It's an incredibly detailed, integrated plan.
It is. And when you analyze it like a consultant, you can see that this entire complex structure with all its pillars and targets really boils down to three make-or-break strategic bets. If they win on these three fronts, they win globally. The first decisive bet is the new materials system revolution. This is the science. They absolutely have to solve the long-standing problems with high-capacity silicon anodes, the swelling, the short cycle life, and they have to successfully industrialize lithium metal anodes. Without that fundamental material science breakthrough, the whole high-energy track just grinds to a halt.
The second bet is about turning that science into a safe and dense product.
Exactly. The second bet is the industrialization of all solid-state batteries. This is the key to unlocking that ultimate prize of intrinsic safety and hitting the 700 Ka density target. It means they have to solve the really fundamental physics problems of the solid-solid interface and figure out how to manufacture these highly sensitive materials at scale. If they can do that, they build a technological moat that's almost impossible for competitors to cross.
And the third and final bet is about turning that technology into actual market dominance.
The third decisive bet is intelligent extreme manufacturing. It's pointless to have the best lab prototype if you can't build it cheaply and reliably by the billion. This whole strategy depends on translating that lab advantage into market dominance with those digital twin-based, hyper-efficient blackout factories. Winning the manufacturing race is what gives you the cost leadership to dominate the market.
Science, industrialization, and digitization. It's an all-in strategy. Which leaves us with a final provocative thought for you to consider. The technical targets here are so extreme, they imply absolutely zero margin for error. If the safety goal is no thermal runaway, and the quality goal is a parts per billion defect rate, will the intelligent L5 self-adapting battery of 2040 be the single most complex and robust mass-market manufactured product ever conceived? A product that has to manage its own complex chemistry perfectly and autonomously for 15 years. It's a challenge that will define the next 2 decades of industrial competition.